Hello, everyone, wherever you are. Welcome to this talk from the Foundation of Data Science series. Today, we are very happy to have Himanshu Tyagi from IISc talk about general lower bounds for estimation under information constraints. So Himanshu asked me to keep it short, so I'm just going to give the minimum. Himanshu got his PhD from Maryland in 2013, I think, after which he was a postdoc at UCSD. And since for a few years, he's been at IISc Bangalore, where he's done a lot of very interesting work spanning cryptography, statistics, and machine learning, among others. So I'm not gonna go further, but hopefully you will see by yourself the breadth and clarity of Himanshu. So please, Himanshu, take it away.
Thanks, Clément, for the introduction, and thanks all the organizers for inviting me. I didn't realize it will be this late, but it's fine. I'm all caffeinated, so I'm up. I guess I'll be up longer than what I intended to. So this talk will be about general lower bounds for estimation under information constraints. And I've fallen in love with this vacuum tablet, so I'll give this talk on this vacuum tablet. Okay. The main points here is general and information constraints. So what we mean is that we will look at the statistical estimation problem, the most basic version of it, parametric statistical estimation problem. Problems such as estimating mean of a distribution, or maybe some other parameter of the distribution by looking at samples from the distribution. But we will look at those problems under information constraints when the samples are not directly accessible, but only limited information about each sample is available. And the goal of this talk is to present sort of very general bounds, which you can use for your favorite applications. And it has taken us some time to converge to this form of these bounds. There are some prior works which we have on related topic, but I think now we have very clean bounds which you can use. And please feel free to ask me questions about how to use them during the talk. And this is joint work with Jayadev Acharya, who's at Cornell, and Clément Canonne, who will be joining University of Sydney soon. And both of them are in the audience, so please direct all your questions to them. Okay, so here is the setup. We are looking at a distributed parametric estimation problem. So what is that problem? Think of this alphabet X. This calligraphic X is my alphabet, and this P theta is a distribution on this X. This small P theta is the density or whatever you have. It's the distribution on this X. For each different theta in this corresponding to this parameter, you have a different distribution. Okay, and we will look at this parameter. This is called a parametric family because you can parameterize a distribution by this theta, and this theta is a finite dimensional set. So just taking some very simple examples, which I hope many of you are aware of. This is the example of This is an example of so-called Gaussian location model, where the observations are real valued vectors, so-called high dimensional vector. Okay, so they are real valued vector, and you are seeing these vectors are generated from a Gaussian distribution with mean theta. And so the parameter space is also theta. And you want to learn this theta by looking at samples from this distribution. Okay. Another example would be I'll give you 3 examples. So second example is the same mean estimation, high dimensional mean estimation, but we can look at product Bernoulli distribution. So now these vectors are plus minus 1 valued, and these are plus minus 1 valued, and each theta I denotes the mean of the ith vector, and they are independent across the coordinates. That's another example. Third example you can think of is the case where this alphabet X is just numbers 1 to D. So you can think of these as some words, and the unknown parameter is the PMF, probability mass function. So the distribution itself is unknown. And this is sometimes called the distribution learning problem, especially in the computer science literature. This is called the distribution learning problem. Okay, so we want to learn a DRE distribution, and we associate this parameter theta with that distribution. Okay, so what do we observe? We observe n independent samples from this unknown distribution p theta. This x1 to xn are n independent samples. And we are looking at a distributed version of this classic statistical problem. These samples are not available at one place. These samples are distributed across players. Each player gets one sample. N players, N samples. And what we are saying is that the player is not allowed to send the sample. I'll draw a picture soon. So the player is allowed to send only limited information about its sample. So what do I mean by limited information? We will provide a general formulation which can capture many such information constraints. And it's a very simple formulation coming from information theory. We'll basically model these channel constraints using a set of, this information constraints using a set of channels. So this channel we are thinking of this channel W as some mapping from this calligraphic X. The domain of the channel is the same as the observation set, and it maps it to some calligraphic Y. So this is the space in which you are allowed to send messages. And this calligraphic W here is the family of channels. So each player T, which has one sample, select some channel WT from this family, and it's allowed to send a YT, which is distributed by this WT given XT, output of WT given XT. So I'm sort of abusing the notation a little bit. I'm using this random mapping and the conditional distribution. I'm using the same notation W for that. Okay. All right. So what kind of channel families will be of interest? Why? What are some examples of such information constraints? So here are two very popular information constraints. The first one is communication constraint. The players are not allowed to describe the samples completely. Each player is only allowed to send L bits about its sample. So these L bits, so this can be captured by this very simple channel family, which has input alphabet X and the output alphabet is just L bit binary vectors. So this captures L bit constraint about each sample. The second constraint, which is also very popular, is a local privacy constraint. Okay. Again, this is the local. So we look at local differential privacy, and that can be expressed by the following channel family. This family is parameterized by this rho. So this is the family of all channels from X to, let's say, all finite length binary sequences. This alphabet is not important here, such that the maximum change in log likelihood ratio when you change the input is at most rho. So this is the so-called differential privacy constraint. So if you change the input from X to X prime, the probability of the same output Y changes by no more than 2 to the power rho. Actually, this should be, yeah. So maybe this should be natural log. For this talk, log is log to the base 2, but who cares about these constants? Okay. All right. So these two constraints are very popular, and so we will look at inference under these constraints. So next thing I should tell you is what kind of protocols are allowed. How are the players allowed to choose these channels from this family as they proceed? So we allow sequentially interactive protocols. When the player T is choosing this channel WT, it can choose this based on what it has seen in the past, based on this past messages Y1 to YT minus 1. And additionally, all the players share this randomness U. So we have shared randomness and we have sequentially interactive protocols. Okay, so all these messages as well as shared randomness is available to a central referee who looks at these messages and the randomness U and forms an estimate of the unknown parameter, theta hat. So this theta hat is our estimate of the unknown parameter. In the classic setting, this theta hat would have been a function of x1 to xn. And now it's a function of the output of that protocol based on the channels that the players have chosen, y1 to yn and u. So how do we evaluate how good your estimate is? We use a loss function. And in this talk, we will look at this LP loss function. Okay, that's a loss function. So when the actual parameter was theta, but your algorithm outputs theta hat, the loss incurred is the LP norm of theta minus theta hat. And we are looking at the min-max formulation where we want to characterize this minimum error under LP norm, expected error under LP norm, which is parameterized by n, the number of players, with each player getting one sample, the channel family W, and obviously the problem that you're solving, the parametric problem. Okay, and I'm saying minimum over all protocols pi. What do I mean by that? Minimum over all sequentially interactive protocols pi. Well, that includes everything we have seen till now, the way you choose your channels and the way you form your estimates. So here is a summary of this formulation. And as I promised, I have a picture for it. So we are looking at distributive parametric estimation under general information constraint. General because we allow general channel families. We allow sequentially interactive protocols. And our goal is to derive a lower bound for this quantity, the EP of NW P theta. Okay. So you, just to recall, you get samples, independent samples from an unknown, from a distribution P theta with unknown theta, and they are spread across the player. Each player gets one sample, and then the players use a protocol pi to choose this channel W's depending on what they've seen in the past. So that protocol produces a transcript Y1 to Yn, and then a referee gets this Y1 to Yn and U and declares the output theta hat. And the goal is that theta hat is very close to theta in LP norm. Okay. If you have any confusion about the formulation, this will be a good time to ask that. I must say this problem has a lot of applications. Jayadev was very particular in saying that we should point out to application. There are many of them. Yeah. Write to us if you use it in some application.
Quick question, Himanshu. Like the channel could be different for different players.
Yeah, exactly. So the players can choose different channels based on, in fact, they can choose that based on what they have seen in the past. It's an adaptive protocol that we allow. Okay. But they must all be from the same family W. Just for concreteness, it may help to keep in mind the communication constraint family. So these WIs are just some functions which you use to quantize your observation. That's the simplest example, I guess. And you can use different quantizers. In fact, you can use it based on the past.
Okay.
So it's an interactive communication protocol for that setting.
So there is a family of channels, but like you can just say like the channel is also parameterized by something, and like I can just update my channel in each iteration.
So for example, these two things, right? So in each player may choose to use a different LDP mechanism, for example, or each player may choose to use a different quantizer based on what they've seen in the past.
Okay,
that's allowed.
Yeah, that clarifies. Thanks.
Okay, great. Thanks. This question I think helps. All right. So we will derive lower bounds for this. So what is the general approach for deriving lower bounds for parametric estimation problem? So here is a program which people typically use to derive lower bounds for the statistical estimation problem. 70 years ago, there was one lower bound called the Cramér-Rao lower bound. And then maybe, 70 is good, 75 or something maybe. And then Lecam has this whole program of deriving lower bounds, which are, I think, in some sense closer to what we'll see today. And of course, these are now very well-known bounds, a very well-known method of deriving these bounds. So what we do is we inside this parameter set theta find a smaller subset of parameters which constitute a difficult case. So we derive lower bounds for this restricted estimation problem when I'm telling you that the unknown theta comes from this one of these theta z, and the z is some I'm just parameterizing it by plus minus 1 valued vectors of length k. So I'll elaborate on this later, why this k is not the same as the dimension of the observation. In some sense, this is the intrinsic dimension of the parameter space. Each coordinate of this zi represents a different dimension of the parameter space. It's just heuristic. Okay. To make it a little bit more concrete, let's go back to our examples. For the product Bernoulli family, this k would be d. Okay, and theta z would be some scaled version of z. This epsilon by root d. That scaling hopefully will become clear soon. This is the scaling which you use to when you are trying to get a lower bound of epsilon for error. Okay, this is a weak loose statement, but some scaling times z. So these are my difficult parameters. If you can solve this, and if you can analyze how many samples will be required to resolve this particular problem, then the lower bound for those samples will apply as a lower bound for the min-max formulation as well. So this is that difficult case. For the discrete DRE distributions, the difficult case is given by this collection here. Maybe this very small picture I can use to describe this collection. So what we are doing is, this is the discrete d-array distribution. I'm dividing my alphabet into pairs, and I'm just using uniform distribution across pairs. So that's, each pair has probability 2 by d. But then I don't make the distribution uniform on the two parts. I make one of them heavier and the other one lighter. But which one is heavier, which one is lighter, is determined by this zi. Okay. So, so for each z, either the first player will be first element of the pair would be heavier, the odd one or the even one would be heavier, based on the sign for each zi sign. This construction is due to Paninsky. This was used by Paninsky to derive lower bound for uniformity testing problem. But it is also, for us, it will be convenient to use this one for learning d-array distributions.
So there's a small comment by Jayadev that, so for the discrete d-array, there should not be a square root d in the denominator, right?
Oh.
It's, in that case, it's epsilon over d, right?
Yeah, okay. Yeah. It's a good comment, actually. Yes, Jayadev. But I can correct things on live now. Okay. And imagine the yellow color is still there. Okay. Okay, yeah. So all of these distributions are at a total variation distance of epsilon from the uniform distribution. I have to take this bracket. 1 plus 1 plus this and 1 minus this. Okay. Oh no. Please just give me 1 second. I've messed up something. Can you see it?
Yes, it's back. Yes.
Great. Okay, so these examples, and now, so the approach is to derive lower bound for this restricted example. So how do we derive lower bound for that? So there are two parts of this derivation. The first part is the standard part. I'm just reviewing this so that everyone is on the same page. This is basically, this part will say that if you can estimate, then you get some information about this. If you can estimate which of these parameters is active, then you can get some information about the unknown z. That's the first step. So estimation implies information. That's how I'm trying to remember it. And this is very similar, in fact, almost the same as what is called Asua's lemma or Asua's method. So what do we do here? So let's make an assumption that if the distance between LP distance to the power p between theta z and theta z prime is some constant, that constant is related to the error, constant times the number of places in which z differs from zi. This is the Hamming distance. So this is some assumption. You can suppose a construction, this theta that construction satisfies this assumption. So this one relates basically loss to the error, the error in estimating coordinates of z. So we make this assumption. And now suppose this z is uniformly distributed over all vectors plus minus 1 valued vectors of length k. And so what you do is you have this z produces the samples x1 to xn under p theta zn. And then you run that protocol pi. Each player uses the pass transcript to choose this channel. And this protocol produces this output y1 to yn. And then the estimator produces theta hat. We add one more step to it. We look at that theta hat and find the z such that theta z is closest to theta hat in LP norm. So I'm calling that closest guy z hat. This z hat is a function of the estimate. Okay. So I can form this z hat. If you give me your estimator, this estimator is given to me by you, and then I add one more step to it to form an estimate for z hat out of it. Okay. So what I will show is that that if your protocol has small LP loss, then the mutual information or the information that this yn reveals about z is at least a constant. That's what I'll show. Okay, roughly that. But in fact, I will show that this average information is at least a constant rather than showing it for the entire vector. That's what I'll show. This is a slight difference from what you may have seen in Fano's inequality. In Asua's lemma, you show that the average information is constant. So here is a simple proof of this fact. I thought I'll give it because it's just these lines. So look at the mutual information. This is the this is Shannon's mutual information between Zi and Yn. The observation and what you are trying to figure out is the ith coordinate of the unknown Z. What is the mutual information between that? That mutual information can be bounded below by the mutual information between Zi and Zi hat, the estimate that you form. Because Zi hat was formed using Yn. So I can always do that. This is called the data processing inequality sometimes. And then you can use Fano's inequality and Jensen's inequality to get this bound. What this bound says is that this sum mutual information is at least k times 1 minus, this is the binary entropy function, of the average probability of error. So I can lower bound the sum mutual information by k times 1 minus binary entropy of average probability of error in estimating Z from Yn. But by our assumption, this average probability of error, the assumption will relate. So this average probability of error is just 1 by k times expected value of the Hamming distance between Z and Z prime, or Z and Z hat. And then by our assumption, we can relate it to the LP loss. And so the conclusion here is that if your LP loss is smaller than epsilon, then the average mutual information that Yn has about each coordinate of Z is at least a constant. This is constant. Okay. Is at least a constant. Okay. So this is the claim. So once your error is small, we know that the average information must be a constant. And therefore, if you derive an upper bound for this average information, that must be at least a constant. And so in the rest of the talk, we'll focus on deriving these upper bound on average information that Yn reveals about each coordinate of Z. So if you want to remember Asua's lemma, you can just remember this part. It just gives you average information bound. If you had used Fano's method, you would have gotten mutual information between Z and Yn instead of this sum. And it's larger than this sum. So this is strictly better than Fano's method. And more importantly, it is very convenient for interactive protocols. Because you can imagine that as you condition on the previous communication, very complicated correlations develop between these Zi's, different coordinates. But now you have to look at one coordinate at a time in this expression. Okay. So next step, this is what we want to do. This is the main step. So now we know that this average information is constant if your error is less than epsilon, and we would like to derive an upper bound for this average information. So what we do is the following. As I said earlier, each coordinate of the Z captures different dimension of theta, the unknown theta. And let's introduce this notation. The Z plus I denotes the vector Z plus I denotes a vector of length k, where the sign of the ith entry of Z has been flipped. So if it's 1, it has been made -1. If it's -1, it has been made 1. That's Z plus I. You flip the ith entry. Okay. So this is a theta Z here. And in each direction, so they are all these parameters on the binary hypercube. And each direction, when you change one coordinate, you get a new parameter. That's the kind of construction we had in the beginning. So keep this picture in mind. So the information about Zi is related to how much this p theta Z, which we can just abbreviate by pz from now on, because this theta is all everywhere. So I just denote it by pz. This pz changes when Z is replaced with Z plus I. So when you change this Z from Z plus I, how much does the distribution change? We need to capture that. Okay, because that will capture how well your output can estimate theta. Okay, so so now I'm sure at some point I used to hate this list of assumptions in statistics papers, but if I claim that we are giving general bounds, I should have assumptions. But you have to take my word for it. These are very natural set of assumptions. Okay, in the sense that these assumptions are basically something which we can verify for a large class of problems. Okay, so what is the first assumption? First assumption is very simple. It says that when you change the distribution from Pz to Pz plus I, that this is the density. If you are thinking of discrete distribution, this is just the ratio of PMFs. If you are thinking of continuous, this is the ratio of densities. In general, this is the Radon-Nikodym derivative, the density of this guy with respect to this guy. So this guy is equal to 1 plus this. So this is the multiplicative change when you go from this to this in density. So it's 1 plus something. So we are just saying that densities exist basically. So it's 1 plus something. And we also normalize this phi zi to 1. Its second moment is 1. By the way, you can check because both of them are density, it must be 0 mean. So it is 0 mean for sure, and its square is 1. This is just a normalization because whatever we have, whatever L2 norm it had is denoted by this alpha. So we took out that part just to normalize it. Okay, so this first assumption is not really an assumption. For all the construction that the example that I gave, this will hold. You just don't have to make degenerate examples. Second assumption is a technical restriction. It's in some sense a shortcoming of our method, but in another sense, it's a mild one. Okay. So what does this assumption say? It says that look at the distribution of the probability of any particular message y. When you change from z to z plus I, when you just change one coordinate of z, that probability the ratio of the change in probability should not be more than some kappa. And kappa is a constant for us. We want it to behave like a constant. So this condition depends on both density and the family. Now, so this is a technical condition. And roughly you can imagine this condition as it says something about how much information can a message reveal about zi. So we are saying it must be bounded by something. Okay. But it holds it holds for many examples. For example, irrespective of which parametric family we are looking at, for this LDP constraint, it always holds. Turns out. And
there is a question in the sorry, Himanshu, there's a question in the chat. I think it's what is the expectation with regard to? So I'm assuming it's what is the random variable here?
Correct. Okay, very good. So this capital X is the random variable. Throughout the talk, capitals are the random variable, small are the realization. So this capital X is the random variable. So this distribution PZ produces that sample X, and then you choose your channel W and pass your X to that. So this is the probability that you see Y, the message Y, given that X was sent on the channel. The input was X. Okay, but X itself is random, so this is the expectation over X, and therefore this is the probability of seeing Y under PZ when channel chosen is W. Is that okay?
Oh, yeah. So yeah, I think there was another question by the. So in the first assumption, the expectation is taken with regard to what? So I'm assuming it's with regard to PZ.
Yeah, that's very important. Yeah, this is with regard to PZ, correct? Yeah, it is customary to take it with respect to the bigger distribution, which is the one denominator here. So yeah, it's with regard to PZ. Good. I think thanks. These are very important questions. Okay, so also this assumption holds for the second one, the boundedness assumption. It holds for all channel families W. For the case of product Bernoulli distribution and discrete distributions. So even there we are in good shape. Now where we fall in trouble is for the Gaussian family, which is obviously a very important basic family. But it turns out that by some gymnastics we can handle that also. But you cannot directly apply a result there. But the bounds that we'll obtain can, in fact we do in the paper, can be used to also handle the Gaussian family. They will not be useful in a plug-and-play manner. You have to do some more work because this assumption doesn't hold for the Gaussian family. May not hold. Gaussian family, once again, for privacy, no problem. But for communication constraints, for example, it may not hold. You can imagine that you can take a part where you declare 1 and another part where you declare 0, just 1-bit communication. And this boundedness can fail there. Okay, so 2 assumptions. Okay, so that brings us to our main result. It looks ugly, but it's not ugly. I mean, not for me for sure. So, so here is this result. So remember, we wanted to bound the average information. So yeah, we are bounding this sum of information. You can divide by k if you like. I'm bounding this sum. It's bounded by some constant. This kappa by 2 is some constant. This n is the tensorization factor because there are n length vectors. Somehow we have used some chain rule or something. I'll show how this n comes. So this n comes. Information grows linearly with the number of observations. That n comes. And that part is there. Second part is alpha square. This alpha, remember, is the alpha from your assumption here. So this alpha captures how much the distribution changes when you change this ith coordinate. So this is sort of the information in x about zi. That's what this alpha is proxy for. So this alpha square is that part. And then this last part, which is the main part for, in the sense, for information constraint. For us, this is the proxy for how informative your channel family is. So let's pass through this last part. So n alpha square and this last part. So what is this last part? It's actually quite nice. So you had this phi z I. So we need max over z. So you can just fix this z, this point that you're looking at. So you have this phi z I and this w channel. This one is sum over all I here. So think of this phi z I as a vector. And think of this guy as a vector, wyx for different y. So it's that part and then normalize by this. And what we will see is that we can handle this quantity. This is the right quantity to look at to capture the informativeness of this channel. So this, it turns out this thing can be handled for many different channel families and for different parametric families. Okay, so this is the main bound. The sum of the mutual information can be bounded by these 3 things: n, the linear growth in number of samples; alpha square, which is the parameter that captures informativeness or the information in x about zi; and this last part, which will now be a proxy for how informative your channel family is. Okay. Allow everything. So yeah, I don't know why Clément said I worked in cryptography. As you can see, I allow everything. You can just send whatever to my computer and I allow it. So I have no clue about security. Okay. Obviously about privacy, nothing about privacy either. So yeah, okay. So proof sketch. First step is just Jensen's inequality. We can show that this mutual information between zi and yn is at most half times this quantity here. But in fact, this first step is a very critical step. Turns out that they were, yeah.
So there was a question. So if k is really large, wouldn't we assume that doesn't go all the way up to k?
Yeah, so the beauty of this expression is that we can derive bounds for it irrespective of k independent bounds, dimension-free bounds. This expression has a lot of structure in it. In the sense that yeah. So maybe we'll come back to this question when we derive bounds, different bounds for it. Maybe that then I can understand the question better.
Oh, and there's another question then on the value of kappa for product Bernoulli. What is the value of kappa that can be taken?
Very good. So for product Bernoulli, we can have it as constant, but for privacy preserving that w rho, this kappa is actually e to the power rho, but our bounds are for the case where rho is less than or equal to 1. That's the regime we were looking for LDP constraint. So there also this is constant. We would like this to be constant. This is something. It's sort of a nagging parameter in our approach that we would like it to be a constant. So all the action should be here. Great. These are very good questions. It's a great audience. So this mutual information is less than equal to this guy. So now this step at the heart of it just uses convexity of divergence. You just express mutual information in terms of divergence and then just view the distributions as the average ones and do some small simplifications and you get it. But it's actually a very critical step. It turns out that there were several prior attempts to handle interactive protocols, and many very, very good papers, which are very good for other results, made this mistake in handling interactivity. And it is, I think, this step which sort of fixes it. And it is not clear if it is a weak step or not, but in all the applications we were looking at, this is not weak. So the heuristic, one heuristic where this step will be tight is we don't lose much if you reveal all the other, in addition to yn, if you reveal all the other coordinates, still you don't get any additional information about zi beyond what yn already gives. If you believe that heuristic is true, then this step is not so bad. That's what roughly we have done by taking out all the conditioning outside. So with this looks like a nice divergence from PZYN to PZ plus IYN. That's all we have to handle now after this step. Okay, so how do we handle? Well, first thing is we want to tensorize things. We want to break the distances or the divergences for n-length vectors to individual distances. That's one thing we would like to do. So we use the so-called chain rule for divergence. It looks ugly, but it gets this conditioning on the past messages. And in fact, this entire line of research for us, one of the star character of this line of research is this chi-square divergence. So we switched from Kullback-Leibler divergence to chi-square divergence. Okay. The nice thing about this chi-square divergence is that it has a nice quadratic form, and it will have a quadratic form in a phi, and that simplifies things. So we switched from Kullback-Leibler divergence to chi-square divergence. This chi-square divergence is the leading Taylor series approximation term of Kullback-Leibler divergence. So in some sense, we are doing some Taylor series approximation. Okay. So we switch to chi-square divergence. Okay. So some expectation over z. Anyway, we'll take a max over this, so no problem here. Some expectation over this guy. Now this is a bit complicated. As this different yt minus 1 come, this is the messages. It changes the past messages, and therefore it changes the channel that the player can choose. And so we have to handle this one carefully. But the interesting thing is this one depends on the past, this distribution. They depend on the past only via this channel wyt minus 1, because the samples were independent. No other dependence on the past. Because we have already taken, this is the distribution given the entire z. If we didn't do this step in the beginning, if we didn't weaken this thing this way, this property will not hold. There'll be other more complicated dependence coming, because conditioning on this past messages will make this z1 to zn, z1 to zk correlated. But because we have weakened the first step, now only depends on the past. Okay, so that's, I think now I'll make just the leap. So what happens? This chi-square turns out you can write an expression for it. Directly you can write this expression. This is p minus q. By the way, if you don't know what this is summation over x for discrete case, px minus qx square by qx. That's one form at least. So this one, because we can handle px minus qx from our assumption, we already had a formula for that perturbation. That brings it alpha times phi zi. But there's a channel also which will enter now, because these are the distributions on the output of the message. So this wyt minus 1 is the channel chosen by the tth player by looking at the previous messages. And so this expression comes up. It's a clean expression now. This summation over x, alphabet was x here. This is summation over y. So that's what this is. This is just the chi-square distance between these two guys. And as I said, It only depends on the pass via the choice of the channel. And this alpha square comes out. This alpha square is from that 1 plus alpha phi. So this guy comes out. Okay. All right. So now we sum over k. We can take this sum inside and you get the sum here. And so if you can't quickly see it, you can just believe me. So you get this expression, what I had promised. Okay. As simple as that. So some loose step where we were taking out things because of convexity, but we think it's not too loose. And then chain rule, and then just switch to chi-square distance. So we get this expression. And the point is that we can handle this expression very well. So here are two corollaries which will give us what we think are plug-and-play bounds, which you can use in your favorite application, and do use them. So the first, these bounds are under some extra assumptions. Okay. So first assumption is, suppose this phi zi I equal to 1 to k are orthonormal, in the sense that we already know that they are unit norm. But suppose they are, if you take the expected value of phi zi and phi zj, suppose it's 0 if I not equal to j. So this is basically capturing the heuristic that these guys capture changes in different direction. And for all the examples that I gave of our construction, this holds. Typically, your construction will have this property. You will have orthonormality like that. Otherwise, that construction is not so nice if you have redundancy of that style. And then, just by Bessel's inequality, this is quite nice. In fact, what you can check is, because this phi z1 to phi zk are orthonormal, and they are zero mean, so even they are orthonormal to 1. These guys are orthonormal. And therefore, if you look at this guy, this is basically just, it's by Bessel's inequality, it's all the thing except that you have removed the one part, or that's the mean square part. So this just becomes variance of this guy. So it's very easy to check that the bound that we have here is just summation over y, variance of this guy. So this is, I guess this is a good point to come back to that comment about what happens to summation over k for large k. In fact, we took it to infinity here. Okay. And still we have a bound in terms of variance. Summation over y, variance of this random variable with easy by expected value. These are the kind of bounds we are looking for, where k will not directly enter here. Okay, so this is the first bound, and this will apply to the cases where they're orthonormal. So let me make some remarks about this bound. So this bound is great for locally differentially private family. So it turns out that this expression that we got, variance by expected value, can be bounded by, for rho local differential privacy, by e, so that log, there should be natural log. Just excuse me for that. So it should be e to the power rho minus, you can show that this is less than equal to e to the power rho minus 1 square.
Sorry, Himanshu?
Yeah.
This is Venkat. I was the one who asked about the k. Could you just go back to the previous slide? I don't think I followed your response, actually.
Yeah, okay, great.
So it looks to me like the bound you have is for each I. If you look at the last but one line. Yeah. But then you have to sum them up over I, don't you? So.
Yes. Yeah. So that.
So there seems to be a factor of little k missing.
No. So this bound is true for us.
Oh, I see. Okay. All right.
Yeah. So you see the sum, and I've expanded. So you expanded to the entire orthonormal basis, and the only term which will be missing is this one term. So you subtract that, and that term actually is the mean. So this becomes variance.
Okay. All right. Thank you. I got it.
Yeah. Thanks. So that's a great catch again. All right. So. Does it make sense now, Michael?
Yeah, I mean, it kind of makes sense. Yeah, this is very interesting. So, I mean, I have to think of it more carefully, but it makes sense. Yeah.
Okay, thanks. Okay, great. So, so now that we have this, and I guess this is a bound which I can just leave as an exercise. You can show this bound. I'm dividing and multiplying with this thing, and the probability sum to 1. And so this is an easy bound to show. If you have local differential privacy, then you can show that this variance by expected value is less than equal to e to the power rho minus 1 square. And this yields tight lower bounds for locally differential private distribution estimation. In fact, even locally differential private mean estimation for Gaussian and product Bernoulli. And the important point is we allow sequentially interactive protocols, and the bounds hold for all p. For all p, this approach will work. Because in some sense, that loss function has been separated out in the ASUA step itself. So this handling different P is already taken care of by that step. That will translate into a constant bound for the mutual information, average mutual information. Okay, that's the first remark. Second remark, in fact, this can be handled for communication constraints as well. And you can show that this quantity is less than equal to 2 to the power L, the cardinality of the output alphabet, which is 2 to the power L under communication constraint. So, and it turns out that for discrete distribution learning, this gives a tight lower bound. This bound is tight for discrete distribution learning, but only for the discrete case. Okay. If some of you have seen these results, and I'll flash them at the end, for the high dimensional case, the Gaussian mean estimation and product Bernoulli mean estimation, the bound that we would have liked to see here was L, not 2 to the power L. This 2 to the power L is too large there. Okay. And now you may wonder how this L can come, right? This looks very sort of, if you see this expression, we have to think about how this L can come. But that's where you can already start guessing that that's where we have to use some sort of inequalities which you may have seen before. I'll show this. This is a second corollary. So now we put some extra assumptions. Suppose this phi z1 to phi zk are independent and sub-Gaussian. Okay. So they have nice tails. Then by using what are called this is this very nice inequality, Gaussian Telegrand inequality. So by using that, it turns out that what you can bound this expression by is the mutual information between this input distribution PZ and W. So this thing is the mutual information between X and Y when X is generated from PZ and Y given X is this channel W. That's the notation. So you can bound it by this. So when we plug this bound in our general bound, we get that this expression here, we had this n alpha square, fine, and this whole thing, it's just mutual information. So first, so this is the bound, which is again very interesting, but similar bounds have been seen before. In fact, there are these strong data processing inequality based lower bounds for inference under information constraints, and this is what we have recovered. You can view this as strong data processing inequality. We were looking at mutual information. Well, you can look at mutual information between Z and Yn, but it's something else. This is mutual information per coordinate, sum of that. And we are claiming that that's less than equal to this output mutual information between X and Y. And we took out some constant and some tensorization happened in the middle. So n alpha square times that. So this is that strong data processing kind of bound. And it recovers that result, but in fact, it clarifies that what takes to get that result. When does that hold? Because those results were derived typically for certain families. And now we know that the assumption, one critical assumption for those families is this one, that they had these perturbations. You can think of these as perturbations, which were sub-Gaussian and independent. Under that, you recover those results. So it turns out that the family that we construct for high dimensional distribution, product Bernoulli, even Gaussian, not Gaussian, product Bernoulli is sub-Gaussian. Okay, so there these things apply, and therefore there we can apply for communication constraint. This guy is bounded by entropy, and which is just less than equal to log of cardinality of alphabet. So we get a bound of L instead of 2 to the power L now. Earlier we had a bound of 2 to the power L for discrete case because the physics were not sub-Gaussian for discrete case. The typical construction, the Panensky construction that we talked about. But for this product Bernoulli case, these guys turns out sub-Gaussian, and we get a much better bound instead of that exponential 2 to the power L that we saw from the Bessel inequality method. Now by this Telegrand type inequality, which I'm not providing the proof of, this is an interesting proof of by itself, not too difficult. This is just L, not 2 to the power L. Okay. Okay, so so this is the second corollary, and I want to make another remark now. This remark is about connection to other bounds. I think some of you may be aware of the classic bound called the Cramér-Rao bound in statistics. And you may wonder how this bound that we are presenting relate to this Cramér-Rao bound. So let me quickly talk about this Cramér-Rao bound. First thing is that this This Cramér-Rao bound works for L2 loss function. So we can work with L2 loss function, no problem. We can work with any LP, we will work with L2. And it assumes an unbiased estimator, at least the basic form. But then there is a generalization called Ventry's inequality that removes this assumption, instead brings in a prior. So we will recover sort of the bound that you get from Ventry's inequality. Okay, here is how we do it. We can set any example. This is our example. We set this theta z to be perturbations around any theta of your choice. So we are modifying the theta by some gamma times z. This is like changing it a little bit in different directions, but with the same magnitude. And we will bring in this thing called Fisher information, which plays a role in Cramér-Rao bound. So this JW theta is the Fisher information matrix for theta when the observation is y, the output of the channel. So it's associated with this channel W. So you have theta, then from theta you generate x, and then from x you use the channel W to get y. This is the Fisher information of theta given y. If you observe y, what is the Fisher information matrix? Turns out, under some minor so-called regularity conditions, this literature is filled with regularity conditions. So we apply that, and under those conditions, turns out that this right side that we have here is exactly the Fisher information. Okay, so in fact, you can write a bound in this form. Sorry, I missed a trace here. It's not the Fisher information. It's the trace of the Fisher information matrix. So the diagonal entries of the matrix. Okay, so this is the bound that we actually had. In the sense that for this particular choice of theta z and under some regularity condition, we get this bound. And you can also worry about the lower bound. Now it turns out that under that, if the L2 loss is less than epsilon, then that ASUA method, the same thing that we did, just one extra step is needed from Pinsker's inequality, you get this bound. And in effect, when you set this gamma, the gamma is a free parameter here, we set it to epsilon by root k, where epsilon is the L2 error that you're allowing. So the bound that you get is that the number of samples needed to get this error epsilon is at least k square by epsilon square times max over all W, the trace of the Fisher information matrix. So it recovers sort of whatever bound you'll get from Ventry's inequality in this setting as well. And I think this method is very nice because if you look at the proof of Ventry's inequality, it is tailor-made for L2 loss. The way it works, even Cramér-Rao bound. Now this one, we have separated the loss function from information. The loss function was handled separately using ASUA method, and the bound is for information separately. So it can work for any arbitrary loss as well. But for L2, it recovers under some smooth conditions, it recovers that Fisher information based bound. Okay, so I think I can conclude now. So this is the bound we want everyone to use. We hope some people use. This bound gives many tight bounds for estimation under information constraints with interaction for all p. It recovers this very nice strong data processing bound. I mean, very nice in the sense the prior work had very nice bounds, and we can recover them. And it also can recover the Fisher information based bound, which also appeared in a recent work. So already there were works which have Fisher information bound. I'll point to them at the end. And there were works which have strong data processing inequality based bound. And now we can recover them and do much more. That's the upshot. So it was the concluding slide, but I have to, I've been saying the bounds are tight. So here is the summary of those tight bounds for all these different problems. In some of the cases, even the upper bounds were not known. So we had to do some small work to get that upper bound. But now everything is tight. Yeah, almost tight. Some stars, you can see some stars here and there. So under privacy constraints, let's just look at maybe this is more interesting. So under communication constraint, what is the so what's the sample complexity? Let's look at L1 distance. So we know that these learning a distribution in total variation distance requires d by epsilon square samples up to an accuracy epsilon in L1 distance. Now it requires d square by epsilon square 2 to the power L. So you get this extra d square, but you get a scaling by 2 to the power L. And when L exceeds log d, then there's no information constraint, and then it matches. The classic case. This is tight. Note that there is this interesting sort of phase transition when you move from this discrete to high dimensional case. This, instead of scaling by 2 to the power L, you just have scaling by L. And we saw why that happened because of sub-Gaussianity, that new bound kicked in. Instead of the variance bound, we had that Telegrand based bound. Okay, that's where it comes from. So essentially in these protocols, what you do is you use different bits to say something about different coordinates. Whereas here you divide the domain, in a discrete case, you divide the domain into some partition of 2 to the power L size and indicate which part it lies in. So you can use whole 2 to the power L, whereas here you can only use 1 bit per coordinate, so to say. So that's, the scaling is very different. And those things are tight.
So Himanshu, there's a question here, which is an interesting question, might be whether it's really necessary for the individual agents to hear what everybody else says. As long as the centralized estimator hears everything, the result may hold even with restricted access at the individual agents. Any thoughts?
So are you asking, is interaction necessary? Is that roughly the question?
No, actually, so Himanshu, it's me again. No, the question is, it seems like it's overkill to have everybody listening to what everybody else says, because they are, the individuals are adapting based on what they hear, but it may not really be necessary for them to hear everything. So as long as the centralized agent is hearing everything, you might still get similar bounds. So you're not really controlling, or you're not paying attention to the information exchange between the agents, it seems.
Yeah, so the upper bounds do not require any interactivity. In fact, private coin protocols attain it.
Okay, so that's good.
Yeah. So, but the lower bound can handle interactivity. That was the purpose here. So, the effort in this talk was mainly about lower bound. The upper bound, in some sense, are straightforward because you show that SMP, simultaneous message passing protocols, attain it, as you were saying.
Okay, that answers the question. Thank you.
Okay, so that was the last thing I wanted to say, and now this talk essentially is based on this paper, and this similar results were obtained in another paper here. In fact, this paper is an updated version of a prior paper. There was a small gap in this paper and some other paper on interactivity, which we fixed in this paper, and now some story about it, in the sense that these two are sort of parallel papers. And in fact, there is very nice line of work on this topic, and I didn't cover any of it. There's a very nice line, there's a very nice set of papers using Fisher information from Barnes, Hahn, Osgood, and Weissman. And even before that, these papers were one of the first ones to look at discrete distribution estimation under communication constraints here. And even before that, high dimensional mean testing under privacy and communication constraints have been studied thoroughly. So there's a long line of literature. Some of the results we have are already there, but many were not there. And in particular, handling things for general W with interactivity for all things, this unified framework is, I think, new. And the reason I didn't do this literature survey as I was presenting is because Clément has made this very nice bibliography of all this work, describing all the details. So you can just go there, click, and find the details. Okay, with that, I'll stop.
Thanks, Himanshu. So if there's any question left, like you can ask them now. And if not, there's also going to be a small off-the-record session if people want to ask questions, but would rather that not be recorded. In the meantime, I would really like to thank Himanshu for giving that talk and staying up so late in order to do so. I don't think it's really easy to upload or signal on Zoom, but yeah, thank you.
If there are any questions, you can also reach out offline. It turns out there is a...
Himanshu, I have a question. This is Acharya here.
Hi,
So I was just wondering if you have some constraints for your estimation, such as unbiasedness, for example. You said that you are generalizing from Cramér-Rao to Van Trees, and therefore you are not, like, you're basically getting rid of that. But if it were there, then would you get something from this with your method?
Unbiasedness, our method, because it's information theoretic, there's no special role I see of unbiasedness right away.
Right.
So Are the upper bound obtained? So you mentioned that those lower bounds are actually achieved by private coins, so not even public randomness, non-interactive protocols. Are there? So just for the applications, are the? I don't quite remember. Are the upper bounds achieved by unbiased estimators?
Not all of them, I think. But
Okay.
I think maybe the Gaussian one is obtained by unbiased, maybe. But I think the question is, are we losing something by going for this? Maybe that is maybe not in the right. I'm not sure. So I've never thought about unbiasedness as a desirable feature because it never distinguishes. It's not. So are you asking, can we show that? Can we show lower bound for the cases where you'll never find an unbiased estimator, where unbiasedness is strictly more restrictive than?
Right.
Yeah, that's
right.
a very interesting point. Yeah. For example, I think for the entropy estimation problem, that thing is there.
Right.
Right.
I mean, I think at some point I mentioned you a specific instance of this, but anyway, I will not go there. That would be too much of a digression.
Yeah.
Yeah. No, but very nice
Yes,
talk. I'm sure to you. I will use it somewhere. I'm pretty sure.
Oh, great. No, so but I must say that many things are general, but some of the things are tied up specifically to the uniform distribution only. So there is scope to generalize further. I think to write a more general lower bound for estimation and information constraints.
So, Himanshu, again.
Yeah.
So I think this question about restricting interaction between the agents might be a bit more subtle. So you're basically seem to be studying two scenarios. One is when there's no interaction at all, which you use apparently for the lower bounds on the mutual information. And the other one when there is a complete interaction, which you use for the upper bounds. That's what I think you said, right? But in these cases, you're studying some kind of maximum over all possible protocols.
No. So what I meant was so lower bound and upper bound for mutual information are all, both those things are a part of deriving the sample complexity lower bound, and that both of them are valid for interactive protocols. In fact, the lower bound for mutual information doesn't require any assumption. That's more or less a single short bound.
No, but I'm just wondering. So there's a specific protocol that the agents use, right?
Right. But
that protocol determines the distribution of what is observed by the centralized observer. So your bounds seem to be for the best over a class of protocols. They don't apply necessarily to specific protocols, as far as I could tell. And so the class of protocols that could result if you had some restrictions on interaction might just be a totally different class somehow.
Yeah, so the only restriction, the restriction that we place on the protocols now so this is the formulation, right? So the protocols that are allowed are where the channels can be chosen based on what is seen in the past.
Yeah, so if what is seen in the past might depend, say, on some graph structure between the agents or some other restriction, then you're dealing with a completely different class of distributions that the centralized observer might see, for instance, right?
So centralized observer sees all of this y1 to yn, and the choice depends on y1. The choice at time t depends on y1 to yt minus 1. That's what we are allowing.
Yeah, but somehow what is said by the individual agent depends on what that agent's information is, right? So
what is then depends on that.
Yeah. So somehow the distributions of the yn, y sup n that result are very much dependent on the assumptions about how much the agents can hear each other, I think.
And they can hear the complete past.
Yeah, so I'm asking about the situation where that might not be the case. I mean, maybe they can only have some restrictions. Whether things would still work in such a scenario.
So I think one of the answers here could be that these xi's are IID. So the player T only gets to see xt, which is independent of everything else, and the past. I think there is no more structure.
Players apparently see the Ys that have been said by the other players. That's what I understood.
Said before, yes.
Yeah, but if that changes somehow, then the whole problem structure.
So I guess what you're asking is, can we derive a lower bound for SMP protocols which is better than this one? Because
that might I might as well show my face. I think if you can see it. Okay. So can you see it now?
Yes, yes.
Okay, yeah, good. So yeah, I mean that might be one way to phrase the question. Yeah.
So
Yeah,
I think
so
there was a
turns out that it is interesting, not for estimation problem, but for hypothesis testing problem. We have such a lower bound which establishes this separation. We have an example where that separation holds. In estimation, currently, we don't have any such example. So we can derive a bound, but we don't know if that bound really establishes a separation of SMP protocols from interactive protocol.
What do you mean by separation?
So can you show that for a particular estimation problem, interaction strictly helps? So that will entail deriving a lower bound for non-interactive or simultaneous message passing protocols that is strictly larger than than what you can do from an interactive protocol.
Okay.
So such a separation, we can derive such a bound for testing problems. I didn't cover testing in this in this talk, but for estimation, currently we don't know of an example where interaction strictly helps.
No, but I think that's very interesting. But somehow this still is studying two extremes, right? Either you have complete interaction or you have none. So I have a feeling that something in between might be interesting too, right? Maybe some graph restricted interaction, and the reason it might be interesting, it seems.
Graph. Oh, right. Okay, now I understand. Yeah, absolutely.
To the extent that I understood what your problem is, you seem to be studying some bounds which are on the class of all possible protocols that could be executed within this class, right? And some of the class changes, then you just talk.
Okay. So in fact, we can't even go beyond sequentially interactive to fully interactive. At least in this talk, I didn't talk about it. This is one round of sequentially interactive. And now you're saying that have a graph between these agents. And yeah, that's a very interesting question, actually.
Yeah, that might be one such thing. I mean, basically to try to control also how much the agents need to hear about each other. Because in a sense, suppose that we're working together in order to make the centralized person have a small estimation error. It might not be necessary for me to hear everything that everybody else says, right? So trying to control that might also be interesting. That was sort of the thought. Yeah.
I think that's a beautiful question, actually. But I don't, if it's a tree graph, I don't think anything will break down because of the way we are just using chain rule, but I have to think about it.
But I think a better way to approach it might be, rather than just fixing a graph and then studying that graph, would be just to ask what do the actual individual agents need to hear to formalize that in some sense, so that they end up doing as well as if they were hearing everything, from the point of view of the centralized estimator. That might be an interesting thought.
I think it's very interesting. Yeah.
But so just to clarify, though, I'm not sure, there might be also some confusion for the audience about what upper bound and lower bound means here. So lower bounds were lower bounds on the sample complexity, and upper bounds were achievability results. So upper bounds on the sample complexity. So for example, we know that for mean estimation, for Gaussian, Bernoulli, and for discrete distribution estimation, even allowing some partial graph structure cannot lead to better bounds, because so if you have no interactions at all between the players, you can solve the task. There's an achievability result that matches the impossibility result, the lower bound, for even sequentially interactive. So yeah, I'm not sure if that's so there might be some task for which there is something in between, but at least for those specific parameter estimation questions, so mean estimation for Gaussian, for Bernoulli, and L1 estimation for discrete distributions, there cannot be anything in between, just because allowing nothing, you can achieve what the impossibility result for allowing sequentially interactive protocols says is impossible. Says you can't do better. So yeah, just to clarify what the upper bound and lower bound here means. It's
yeah, I think it's so. I was a bit fast about this part, that what will we actually derive. So we can treat it as a sample complexity lower bound or a lower bound for this min-max error. An algorithm will give you an upper bound for this, because it's min over pi, and a converse bound, what we are doing here, is a lower bound for this, and which can be translated into a lower bound for sample complexity if you are looking for a particular error epsilon. Okay.
I'm gonna take us offline.